In this sequence, we're going to look at the row 2 sequence from N2 to F2 and then the breaking apart of the F2. On this sheet, we're going to look at the NO plus, add an electron to become NO. And then we're going to add an electron to the NO, the nitric oxide, to go to the NO minus, which is the same as oxygen. So if we take a look at this structure here, the nitrogen, this is a sigma bond, this is a pi bond, front to back, p orbital here, you get p orbital overlap. That is the traditional p orbital. Here we have a p orbital vertical for the nitrogen, have a p orbital vertical for the oxygen. You get overlap, another traditional pi bond. Pair electrons, you got sp hybridization, sp hybridization. Now, in the textbooks, and mostly what you see is some variation of this, where apparently the electron comes in, and some people suggest that you have a 3-electron bond here. I'm saying that it can come into this p orbital, and as it comes into this p orbital, that is going to cause as it comes into this p orbital, this electron moves over, and you get that. So that would give this pair of electrons here. You can see, and this make this a p now. You got the pair of electrons here. This one I'm showing an electron in the p, and that's what you see many times in the book. You'll see a electron dot like this for the sigma and the pi, and put the electron on the nitrogen, and then you have a pair and a pair, and you have sp and sp. That is not what happens. It cannot happen because it does not fit the data. The bond order, the bond length shows a bond order of approximately 2.5. So what does happen? Well, actually, it's a little bit simpler, I think. The electron, let's suppose it comes into this oxygen, but now the electron moves over, so now maybe you do have this p orbital, the oxygen p orbital here, but you have a pair of electrons in it, and these pair of electrons with this sp, the p electron sp, will hybridize to give you a pair of electrons, sp2 and sp2. And evidently what happens is that this p orbital stays bowed. This stays bowed, and the electron is into the pi region. So this is what we're showing that's going to happen to give the correct structure. So actually it's simple. It's just this electron in the p orbital pulling back to the oxygen, hybridizing, and this one stays in the p orbital, but now the p orbital is no longer a p orbital, it's a pi, because it's moved into the pi region, and that's due to the small electronegative character of the oxygen. Now, so what would the electron dot be, and what we have in this case? Got a pair of electrons on the nitrogen, showing it here. You got a sigma, usually the one in the middle. You got a pi, traditional pi, front to back here. You have a pair of electrons here, pair of electrons here. That'd be sp2. You have sp, and then you have this one long p orbital pi. You have one electron in it, and I like to show it as a dot, and then dot, 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 showing it as one electron bond. And this fits the data. And this sort of makes sense that it's not all that complicated, that it just stays in the relative position as it is. Now, this is NO, nitric oxide. What happens if we add an electron to NO to get an NO minus? And this is a very common sequence, NO plus to NO minus. I'm suggesting that, again, this electron takes and comes over to now the nitrogen. And this is going to cause this one electron that sort of belongs to the nitrogen to move over. So now we have a second electron pair on the nitrogen, and electron pairs tend to hybridize sp2, so now you got the mixing of, you got the pair of electrons in this P and pair of electrons here, and they hybridize to give you the sp2 nitrogen. What happens is, again, evidently the p orbital of the oxygen is still in the position it is, where the electrons can be left in a pi region. So what we have now is, this is what we had before for the nitrogen, but now you only have a sigma bond plus a 1 electron pi, and now the electron here is front to back in a p orbital pi. It's actually pi because it's in the pi region, but it's for the p orbital both. And that would give us an sp2 oxygen, sp2 nitrogen. What would the electron dot be? Again, nitrogen, oxygen, this would be sigma, the sigma here. Then you have pair of electrons, pair of electrons, pair of electrons, pair of electrons. You have the 1 electron pi, which would be this one I'm showing, because it's showing it belonging to the nitrogen. This is it here. But also you have one now on oxygen, and these are 90 degrees to each other. If we go further through this sequence of NO to NO2, and then from chlorine to chlorine oxide to ClO2, I think you'll see more reinforcement for this kind of thing happening. In this session, we're going to continue. We're going to look at the oxygen, O2. Here we have an sp2 oxygen, top, up and down, back and out front. This is a 1 electron p orbital pi, up and down, and then front to back you have one that'd be oxygen. What is going to happen if we take and add an electron to the structure? Let's say we add it to here. And what's going to happen now is that this is, you can show it in a P, you can show it going into a P, but that's not going to stay. That'd be high energy. These 2 electrons now is going to hybridize, and you're going to get an sp3 oxygen here, 3 pair of electrons. You got O2 minus 1. This one's sp2. This is superoxide. So I'm going to come down here and put this structure again, and we're going to show 1 electron coming in. Where does that 1 electron go? Well, I suppose it comes in and does the same thing, comes over to here, and as it does, now you got a pair of electrons, and again, it's not going to stay in the pi region. It's going to, you can show it in the P, but that's the high energy, and what it's going to do is hybridize, and so now you've gone from -1, O2 minus 1, to O2 minus 2, and these oxygens, the electrons are going to hybridize sp3, sp3. That's what you have. Now, that electron, number of valence electrons here, 14 is the same as N2. And so now I can switch N2 here, and we have a single bond. We're down to 1 single bond. And again, as the one electron comes in, it can come to here. One of these can come to there. And what happens is you've broken the single bond, and you can get F0, fluorine atom, which is very high energy, is going to gain an electron, but we're just looking at 1 molecule and adding 1 electron. And here you get the, for a pair, the F minus, full F minus. And that is going to be atomic. These are atomic, and it has the same number of electrons as Ne, neon, the noble element. Neons, that's what's going to happen. In this session, we're going to look at models. We're going to look at a model of NO plus, add an electron, which will go to NO. Then the NO, we're going to add electron. We go to NO minus. Now, NO minus has the same electron configuration as oxygen as we've seen before, so it will switch. But this NO plus, NO minus is a well-known system. We take the oxygen, we add electron, we get O minus, which is superoxide. We add electron, we get O2 minus. This is also a well-studied, well-known mechanism and a pathway. And this is equivalent to F2. We take and add electron to F2 and we to atomic. So we've gone from the left side of the periodic chart to the middle. So we start at the middle, and then you go over to the noble element. Okay, so here's the model that we have. It's not perfect, but this is the nitrogen. St hybridized with pair electrons. The oxygen in NO plus is St hybridized. You got a traditional pi front to back, a traditional pi top to bottom, if you will, and this uses sigma. So what I'm showing here is I'm showing another electron. We're going to take and add the electron. Where does the electron go? Well, if you look at the formal charge, you got 2, 3, 4. You see the 2, 3, 4, 5. You got the positive on the oxygen, which you got the triple bond. So I'm going to say that the electron comes in at this pi system here, this p orbital of the oxygen. Now, what's going to happen? You're not going to end up with a 3 electron bond. That's not what's going to happen based on the evidence. What's going to happen is that this p orbital is going to break away. So let me see if I can. Okay, so it's going to break away, and it's not going to stay. This will be a high energy state. It's convenient to look at the intermediate state sometimes. So now we got a pair of electrons in this P, pair of electrons here. So now I got 2, 4, 5, 6, and half of 5, 6. But this is not going to stay. As I say, it's an excited state, and this sp electron pair and this p orbital pair is going to hybridize. So you're going to lose the traditional p, and now it's going to take and move over into your BSEPR structure, the trigonal sp2 hybridized oxygen, and that is going to look like this. So here I have the model. Again, going back, you can see the similarity here. We've got them here, and this one here is going to hybridize. So now we have the NO. The oxygen is sp2 hybridized. Got a pair of electrons, a sigma pair, a traditional pi, and now you have just this one electron pi system, which is if it excites you to go back to a p. But this is what you have now. So what can happen to, and this is NO, this nitrogen is sp hybridized. So what can happen now to the NO? We can take and add electron, and I'm showing it coming over here and adding at this pi, the p orbital of this nitrogen. It's going to break the pi. It's going to break this pi simply by this p orbital pulling out of that double bond. This is what the evidence shows. So let me take and see if I can get this one to sort of do what's going to happen based on the evidence. Based on the evidence, not what I'd prefer, but based looking at the evidence. And again, you're going to get a P here temporarily, and that would be a high energy state. Okay, high energy state. And so now, what are we going to have? This is your sp2 oxygen. This nitrogen, you got a pair of electrons, but as we saw before, we don't expect this to stay. It's going to hybridize, and so you're no longer going to have the p orbital. So I'm going to take this part of the p away, and again it's going to move up. You're going to get the VSEPR shape. This is going to move up into this region. So what do you have now? You have the NO minus, which has the same valence electron as the oxygen. So let's see if we can see the similarity, what's going to happen between let's do it this way. Let's try to be consistent here a little bit. Look at it this way. And so what you're going to do is this is going to hybridize, and now you have the O2. So looking at the O2, basically what has happened from NO plus to the O2, you just had pairs of electrons pull over into the P and hybridize, and you end up with this shape where you got 90 degrees of each other. Now this is the ground state oxygen. The higher energy oxygen would be where this would just simply rotate 90 degrees and you get pairing of electron pairs. But that's not happening. So what's going to happen now, if we bring in another electron, we're going to get the same type thing that's going to happen if we bring in another electron at this position here. It's going to do the same thing. It's going to go to the P and then hybridize. It's going to hybridize to an sp3. So this would be an sp3 oxygen. Looking at the one on the right, this would be a pair of electrons in a P, but it's going to hybridize to sp3. That's what's happening. This would be the superoxide, and then if you take and add another electron, it's going to come over here and get the same thing. You get O2 minus, which is equivalent to F2. That appears to be what's going on. We're going to look at the summary of the row 2 elements from the maximum bonding, say N2, or in this case we look at NO plus. It's got 10 valence electrons, 11 for the NO, 12 for the NO2, 13 for O2 minus, 14 for O2 minus 2, 15, you split the F2, if you will. The F2 is isoelectronic with this, into atoms. The bond order for the N2, or Cn minus, or CO, but here we're looking at NO plus, is 3. The bond order for the NO is 2.5. Here the paramagnetism is 0 for the N2 or NO plus. Here we have one unpaired electron. Then we'll go to oxygen O2, where we have the bond order 2.0, and in one form you have two unpaired electrons. This is the ground state, and then you also can have an excited state for oxygen where the P number of paramagnetism unpaired electrons is 0. Then we have 13O2, the bond order is 1.5. Again, there's one unpaired electron, paramagnetism is 1. The F2, the bond order is 1, and there's 0 unpaired electrons. So you can see the sequence here for the bond order 3, 2.5, 2, 1.5, 1.0, and then you have atomic. Hybridization, sp for the nitrogen here, sp for the oxygen, sp for the nitrogen and nitric oxide, sp2 for the oxygen. For oxygen, sp2 and sp2. The O2 minus, which is sp2, and one's sp3. The O2 minus 2, now they're sp3, sp3. And then over here you have the atomic. You could have the fluorine atom, or in case of adding electron, F minus. These are the isoelectronics we pointed out. For O2 minus, you can have oxygen fluoride, And of course O2 minus is F2.